Happy, happy, joy, joy, happy, happy, joy, joy, happy.
A wintertime region of rock and wind and snow. A rugged world of cold and isolation. Yet the snows that blanket this remote part of the San Juan Mountains are a treasure to all living things. In spring, the snow will melt to water the land, to fill the brooks, the creeks, and the rivers. Downstream, the waters form tributaries of the Colorado River, where man-made dams and reservoirs even out the erratic flows. If enough water can be stored in these reservoirs, cities of the Colorado River Basin states will not thirst. The crops will not wither. But water demands grow daily. Already, the Colorado River is inadequate to meet the expectations of early-day planners. Man looks to his own efforts to increase the flow of water. Since the 1946 experiments of Dr. Vincent Schaefer, we have known that some clouds can be modified through seeding to yield additional precipitation. But reliable seeding techniques were hard to develop. Sometimes seeding worked, and sometimes it didn't. In 1961, Congress directed the Bureau of Reclamation to begin a long-range study of cloud seeding with the aim of eventually augmenting the nation's supply of water. The program, called Project Skywater, continues at many sites throughout the United States. Enough is now known from field experiments to conduct a pilot project where test results are applied to a more extensive area. The Colorado River Basin was selected for the first major pilot project. Investigation showed that the San Juan Mountains in southwestern Colorado offer many suitable cloud seeding opportunities on clouds that form when moist air blows in from the southwest. Generators placed upwind could provide silver iodide particles that will flow with the air rising over the range. A storm with low-speed winds could be seeded from generators a few miles away. High-speed winds would require use of generators farther from the mountains. Research has shown that temperature is critical. Maximum snow crystal growth occurs at -15 degrees centigrade. If the cloud is too warm or too cold, seeding is not effective. The very tiny silver iodide particles act as nuclei around which moisture from the cloud will freeze. After a silver iodide particle has been in the cloud about 15 to 30 minutes, the snow crystal which has grown around it is large enough to begin its fall to the ground. Scientists who designed the pilot project for the San Juans built a model in a wind tunnel to study air currents over the mountains. 33 silver iodide generators were then installed in selected positions upwind from the 100-mile-long target area. The time is dawn. On a hill overlooking Durango, a Raywin sonde is lifted aloft by a helium-filled balloon. The Raywin sonde gives readings on temperature, pressure, humidity, wind direction, and speed as the balloon carries it to high altitudes. Meanwhile, in Denver, a computer collects weather data from points all over the West. In the memory disks and in the tapes is formed a continuous picture of weather as it occurs. The picture is then transmitted by telephone lines to all experiment sites of Project Skywater.
You know, the snowpack and avalanche criteria are within the safe limits. Looks like precip's going to begin this afternoon about 4 p.m. is my best.
To measure seeding effectiveness during the research period, only half of the acceptable storms are seeded.
Cruise Mike, initial altitude to 2,000, visual, clear for takeoff.
The first real demonstration that man was able to alter the course of the weather came a little over 20 years ago. In 1946, two scientists in the United States discovered that by dropping pieces of dry ice from an aircraft into a cloud, they produced a snowstorm. The idea was immediately taken up in Australia by the CSIRO Division of Radiophysics, and experiments were soon underway to find out whether extra rain could be stimulated by this method. The trials took place on days when there were a number of separate but similar clouds in the same general area. A check was first made by radar to see whether any of the clouds already contained raindrops. If there were no raindrops present, then a hundredweight or two of dry ice was tipped into the top of one of them. These experiments were successful. When conditions were suitable, most of the clouds which had been treated with dry ice rained soon afterwards, while the other clouds around did not. But it was soon realized that this would not be an economical method of making rain over a large area. It would mean that many tons of dry ice would have to be taken to high altitudes above the cloud tops.
It was an American scientist, Bernie Vonnegut, who first suggested that silver iodide be used instead of dry ice, and perhaps much less of it would be needed. To understand how silver iodide can induce a cloud to rain, it's first of all necessary to know something of the nature of clouds themselves. The sort of cloud that we're interested in is formed in the first place by air rising up and the moisture cooling and condensing in the form of minute water droplets. If we could take a microscope and have a look at a portion of this cloud, we would find that these droplets are so tiny that it requires about 1 million of them to form one raindrop. They're so light that they appear to float in the air, going up and down with the air currents. The temperatures in these clouds are frequently below freezing, but the droplets are still in the form of liquid water. How then can a raindrop, which requires 1 million or more of these tiny droplets, be formed? One way involves the formation of ice crystals. If an ice crystal forms in a cloud which is below freezing point, it grows rapidly at the expense of the surrounding water droplets and becomes a snowflake. The snowflake grows as it falls through the cloud. Pieces may splinter off, and these grow into new snowflakes. In most parts of Australia, these snowflakes melt as they fall through the air at lower levels, and rain is produced. Now, these ice crystals form in the first place in the presence of ice nuclei, minute particles which have the special property of starting the freezing process. Sometimes there are enough of these nuclei present and the clouds rain of their own accord. If there are not enough natural nuclei present in the atmosphere, it is possible to seed the clouds with artificial nuclei. So far, silver iodide crystals have proved to be the most effective and convenient artificial ice nuclei. If we burn a solution of silver iodide, enormous numbers of minute crystals are formed. These are so small that they form an invisible smoke. The crystals are similar in structure to ice crystals and act as ice nuclei, providing an excellent trigger for the rainmaking process. In a real cloud, the ice crystals would continue to grow as they fell through the cloud until they melt and become rain.
Some of the first trials with silver iodide were made with burners placed on the ground, the idea being that the smoke would be carried upwards by air currents to the cloud level. This method was unsuccessful because the smoke rose only very slowly, and if it ever reached the levels of supercooled clouds, it had by that time lost most of its ice nucleating properties due to exposure to sunlight. This difficulty was overcome by generating the silver iodide nuclei with burners fitted to the wings of an aircraft. In this way, the ice nucleating crystals were carried right into the clouds before they had time to decay. The seeding solution was pumped to the burners on the wings, where it was ignited by a spark plug.
These trials gave much the same results as with dry ice. When conditions were suitable, the seeded clouds gave several times more rain than the unseeded clouds. But much less silver iodide was needed, and it was not necessary to climb above the cloud. With cumulus clouds, which are formed in rising currents of air, the smoke can be released at the base in the up currents and is soon distributed throughout the rest of the cloud. And if the temperature at the top of the cloud is cooler than -10 degrees centigrade, then rain usually falls about 20 minutes later. With stratiform cloud, however, the updrafts are not nearly so intense. If the smoke were released at the base, it would take very much longer for it to be distributed throughout the cloud. So, seeding is done directly at the -10 degree centigrade level, and the rain usually falls from half an hour to 3/4 of an hour later. For successful seeding, for both types of cloud, the depth of the cloud should be at least half the distance from the ground to the base of the cloud. Otherwise, if rain were stimulated, it would tend to evaporate in the drier air underneath the cloud.
Rain-making trials with silver iodide were first carried out over large areas in the 1950s. Specific regions were chosen in various parts of Australia where the rainfall over a seeded area was compared with that over an unseeded area. These trials showed that rainfall can indeed be increased in areas where the climate is suitable, such as on the inland western slopes. And during the course of the experiments, more was learnt about the physics of clouds. But several new questions arose. For instance, there was strong evidence that the effects of seeding tend to persist even after the seeding has ended.
It seems most unlikely that silver iodide smoke will remain in the seeded area for more than a few hours or days at the most. And yet the increased rainfall following seeding tends to persist for weeks or even months. We don't yet fully understand this unexpected result, and the causes of it are still being investigated. However, there is an old saying that rain begets rain and drought begets drought. This is borne out by the records, where it is seen that rainfall patterns tend to persist for a long while. So it is possible that increases due to seeding may persist by a similar mechanism. In order to investigate these effects more fully, a new large-scale experiment was started in Tasmania in 1964. A target area was selected in the Central Plateau region. This was of particular interest as it forms the main catchment of a large hydroelectric scheme. Extra rain here would be of great value, as it would add to the water available for generating power. Clouds in the target area are seeded or not seeded on a random basis, and the rainfall in the target area is compared with that in the two control areas on either side of the central target area. These control areas are never seeded, The comparison of the area rainfalls will then show whether the rainfall in the target area has been increased or not. This whole operation is carried out in alternate years, but the rainfall measurements are made in all years. So persistent effects of seeding can be investigated as they rise and fall away following the start and the end of seeding.
The Tasmanian experiments are being conducted by CSIRO in collaboration with the Hydroelectric Commission. During a seeded year, the cloud seeding officer in Hobart gets regular forecasts from the Weather Bureau. A specially fitted aircraft is used, and there are 2 crews, each consisting of a pilot and a cloud seeding officer, who also acts as the navigator. If the right supercooled cloud systems are approaching the target area, the decision is made for the duty crew to fly. During the climb, the cloud seeding officer plots the temperature at various levels and measures the depth of the cloud. Once he knows the direction of the wind and its speed, he can calculate where the silver iodide should be released so that the rain will fall within the target area. The silver iodide solution is pumped to the burners on each wing and ignited. Rain gauges are placed at regular intervals throughout the target and control areas. This rain gauge at Bronte Park is in the target area. Like the others, it is read every morning at 9 o'clock. All daily readings are sent to the Bureau of Meteorology. Since no one at the Bureau knows when the target area was seeded, there's no chance of bias in working out the total rainfall in each area for any particular period. The Tasmanian trials are still going on. When they're complete, it will be possible to calculate how much extra rain was caused by seeding. In the meantime, the results of 20 years' research in scientific cloud seeding are now being passed on to state governments for use all over Australia.
And it's now clear that there are many parts of Australia where clouds suitable for seeding occur reasonably often. And it's quite clear that the right methods of seeding can induce them to increase the rainfall. In this course, we aim to give you 3 things. First, comprehensive account of the background of cloud seeding and its physical basis. Second, a description of the methods that we use. And third, how you can apply them in various parts of Australia.
New South Wales, Victoria, South Australia, Western Australia and Queensland all conduct cloud seeding operations. It's often a collaborative affair between several government departments.
Meteorology. Could I have the cloud seeding forecast for the Waterworks catchment area, please?
Oh yes, Con. The southerly stream this morning is quite cold and unstable. Suitable cumulus cloud today.
4/8. Base 2 to 3,000 feet. Tops 10 and some as high as 15.
The winds at 5,000 feet southwesterly at 30, at 10 southwesterly 40, and at 15,000 feet west-southwest 60. The freezing level 7,000 feet, -5, 10,000, -8, 11, and -10, 12,000 feet.
Specially fitted light aircraft can be ready at short notice whenever conditions appear suitable. The target may be a water catchment, a wheat crop, undergrowth on a forest floor. The procedure is the same. The clouds are seeded upwind from the target so that by the time the rain starts, it will fall where it is needed. Exactly how much the rainfall can be increased is still the subject of critical assessment. In places where suitable cloud systems don't occur, even the best cloud seeding methods cannot produce rain. It's in the areas of light to medium rainfall that the best prospects for rainmaking lie. In the wheatlands of the Mallee, a half-inch increase in the rainfall seems quite possible. Falling during the growing season, this could add something like $2 million to the value of the wheat crop, a worthwhile return certainly for an investment of several $1,000s. And there's no doubt about the value of additional rain for generating hydroelectric power and for damping down forest areas to reduce the hazard of bushfires. What we already know about cloud seeding is being actively applied, but new techniques need to be developed. For example, for treating types of clouds which don't react to silver iodide. And so the research is still going on. We need to know much more about the natural behavior of clouds and to understand more fully the basic physics of clouds and rain. Such fundamental research will always be an essential part of any successful method of rainmaking.
My name's Todd Flanagan, and I'm the project meteorologist for the South Texas Weather Modification Association in Pleasanton, Texas. I always had an interest in severe weather, thunderstorms, hurricanes, tornadoes, that sort of deal. So in 1995, I moved to Lubbock and did my 3 years at Texas Tech. I got my master's in '98, and it just so happened that the project here in Pleasanton was just starting up and they needed a meteorologist.
Tim Pickens. I'm Chief Pilot for the South Texas Weather Modification Association here in Pleasanton, Texas. We do rain enhancement for South Texas region and San Antonio.
I don't know if you can see that, but what I'm looking at is right underneath here. There's a little shelf. See it? Okay. That's what I'm looking for.
When the pilot finds the right kind of lift, which would be 500 feet per minute or greater, then he's got a button he pushes and one by one we can fire off the flares. The flares contain silver iodide, and the reason we use silver iodide is because the structure of one particle of silver iodide is the same as like a crystal of ice. They're very similar. So the thinking was that, well, if that's the case, maybe when we put these particles up into the really cold parts of the cloud, the water vapor is attracted to the silver iodide particles and it starts to grow into a snowflake. Because remember, this is high up in the cloud where temperatures are below freezing. So these snowflakes will grow and like take away the water vapor out of the cloud. And of course, when the flakes get too big, they start to fall. And as they fall through the warm part of the cloud, they melt and turn into raindrops.
Now, something I've noticed here since I have moved here, since I've started cloud seeding, is here, I live here close to the airport. I probably put 4 roofs on my house in a 5-year span from hailstorms here. But cloud seeding in the right fashion prevents hail. And it increases the rain and prevents the hail damage. Since I've been cloud seeding, I have not put a roof on my house. And we've had hailstorms, and over in Devine we've had massive hailstorms. At that particular time, Devine wasn't in our district. So whether or not it's a given, if you get on the cloud early enough and you start seeding it early enough, you could prevent lots of different things besides increasing the rainfall. Our meteorologist could tell you more about that.
Our meteorologist can tell you more about that.
The whole idea with hail suppression is to just put a lot more particles in there to reduce the size. Because if you have 100 million particles versus, say, 100,000 particles, the 100,000 particles have more water vapor to work with. It can grow a lot larger versus 100 million. So you put the 100 million in there, and instead of getting golf ball size hail, you may end up with pea size hail. There's a lot of, I have some friends, you know, that I've gone to grad school with or undergrad, and they're like, weather mod, why would you want to do something like that? Because weather modification is kind of like the black sheep of the meteorology field, I think. And a lot of people just scoff at it because, you know, there's never been concrete proof that it works.
There's never been concrete proof that it works.
This is pretty much your flight track there. There. Okay, you're taking off now, so this is your flight. There you go. And that's the storms now. So, but this is all heading toward Pleasanton, so we're going to get rained on here in a little bit.